right, and our fourth speaker is Tchetgen from Harvard, who will be speaking on the negative control approach to detect and control for unobserved confounding.
Thank you. Thank you for having me here. So I'm a biostatistician and epidemiologist, and so I live in two worlds, one where I work on methods and the other one where I actually apply them to observational studies. And I'm going to talk about negative controls today. We've heard a lot about observational studies, the main method of adjustment that has come up to get rid of bias in observational studies that has been mentioned throughout the day has been measuring all common causes of the exposure and the outcome of interest and adjusting to that for them somehow. The challenge is that often you do not know whether you have all of the common causes. There's no of the exposure and the outcome. And there are a lot of work that has gone into relaxing that assumption by perhaps changing the design of the study or measuring other variables, adding some structure to the problem. I'm going to talk about one that comes from experimental biology, known as negative control, and that has made its way into epidemiology in recent years. So non-causal association in observational studies may be classified into three categories. In addition to chance, it could be mismeasurement, we call bias, which is notorious in case control studies. Confounding, that you have a non-measured common cause of the exposure and the outcome. Of course, there are only two reasons why two variables could be correlated, could be associated. Either one causes the other, or there's a third variable you haven't accounted for that correlates the two. And so we want to, of course, learn about the former reasons, and we want to rule out the second reason. And the third source of bias could be selection of individuals into the analysis that may distort the association in such a way that you may find one when there is none, or you may not when there is one. In experimental biology, the manipulation of experimental conditions prevents many of the non-causal association that arise in observational studies. So they're onto something, and let's see nonetheless, experimental biologists routinely question whether they have correctly inferred causal relationships from the result of their experiments. Biologists employ so-called negative controls as a means of ruling out possible non-causal interpretation of their results. So let's see how that works. Consider an example where we're interested in the hypothesis that a particular cytokine enhances the killing of a species of bacteria by neutrophils, a class of white blood cells. An experiment is devised in which neutrophils, bacteria, and growth medium are mixed together. In condition 1, the cytokine is added, and in condition 2, some inert substance such as saline solution is added. After incubation, the bacteria are enumerated, and the number of live bacteria compared between the two conditions. Fewer live bacteria in condition 1 than in condition 2 is consistent with the hypothesis that the cytokine enhanced the neutrophil-mediated killing. Nonetheless, concern often remains that something other than cytokine-aided neutrophil-mediated killing may be responsible. For example, you may have a contaminant in the cytokine preparation that directly kills the bacteria. You may have perhaps the cytokine itself kill the bacteria, or perhaps some other unintended difference between the treated and untreated conditions, example, temperature or pH, cause the differential survival of the bacteria. Each of these unintended differences is broadly similar to what we call in epidemiology confounding, a characteristic associated with the exposure, present of the absence of the cytokine in this case, and causes the outcome differences in the bacterial counts in this example. So how do they address this issue traditionally in experimental biology? Well, they do two things. They attempt to eliminate unwanted differences between the compared groups in the design, and further to measure and account for any unavoidable differences in the analysis stage. The second general approach is to perform negative controls, and they come in two flavors, negative control exposures or negative control outcomes, to repeat the experiment under conditions in which it is expected to produce a null result and verify that it does indeed produce a null result. So it's very intuitive. Several strategies are employed to design negative controls. For instance, you may leave out an essential ingredient, the neutrophils in this case. This negative control could produce fewer bacteria with the cytokine than without. Inactivate the hypothesized active ingredient by adding specific antibodies that neutralize the cytokine. Check for an effect that would be impossible by the hypothesized mechanisms. Use a species of bacteria completely impervious to the actions of neutrophils. There are, of course, a list of possible non-causal explanations for an experimental result are almost endless, and so is the list of possible negative controls. Judgment is required to assess how many such non-causal explanations are plausible and which negative controls are of greatest value in ruling out key threats. So here's a directed acyclic graph that depicts what we're concerned about, the unmeasured confounder of the effect of an exposure on an outcome, and you may have observed some confounders that you would adjust for. And so in epidemiology, there has actually been, negative controls have actually been used in epidemiology to detect confounding and other sources of incorrect causal inferences, and I'm going to give you a few examples. Observational analysis of the effect of vaccination in the elderly suggests a remarkably large reduction in one's risk of pneumonia related hospitalization, and also in one's risk of all-cause mortality in the following season. This large observed effect, combined with the lack of measurable vaccine effect in ecological studies, have led to a suspicion that uncontrolled confounding has exaggerated the impact of influenza vaccination on mortality and on hospitalization. In a very famous paper, Jackson et al. In 2006 implemented a negative control analysis, and they were very clever. What they did, for the first negative control, they actually did two types of analyses. The first negative control outcome, the authors used the fact that vaccination often begins in the autumn, the fall, while influenza transmission is often minimal until winter. Thus, they could assess the risk of pneumonia, influenza hospitalization, and all-cause mortality among vaccinated versus unvaccinated, both before, during, and after the influenza season. The only biological plausible mechanism by which influenza vaccine could protect against mortality or other related hospitalization is by preventing influenza itself or its consequences. Therefore, Jackson and colleagues reason rightfully that if the effects measured by prior studies were causal, it should be prominent during influenza season. If instead it were due to confounding, then the protective effects should be observable immediately after vaccination, but before the actual influenza season. So what they did in a cohort study analyzed using a Cox proportional hazard model, I'm not going to go into the technical details, despite efforts to control for all the measured confounders, they observed that the protective effects was actually greatest before, intermediate during, and least after influenza season. They concluded that this is evidence that confounding rather than protection against influenza accounts for a substantial part of the observed protection. The use of this negative control outcome approach is formally similar to the leave out an essential ingredient control design described prior in the experimental biology literature, as influenza is essential in the proposed causal pathway. Second, Jackson et al. In their 2006 paper postulated that the protective effects of influenza vaccination, if real, should be limited to outcomes plausibly linked to influenza. So this is related to Hill's guideline on specificity. And so what they did is they found that influenza vaccination was also protective against injury and trauma hospitalization. This too was interpreted as evidence that some of the protective observed effect for of the vaccine was due to unmeasured confounding. The second negative control outcome is formally similar to the check for an effect impossible by the hypothesized mechanism approach described in the experimental setting. Epidemiologists also sometimes use, so those are two examples of negative control outcomes, and you could also have, I'll give you an example of negative control exposures. that have been used in epidemiology. One such explicit application of this approach relates to the use of paternal exposures as a negative control exposure to maternal exposures considered to have intrauterine influence on offspring's outcome. And this is George Davis Smith in a very nice series of papers in 2011, 2012. Paternal smoking was used as a negative control and may show associations with offspring outcomes similar to those of maternal smoking if the associations are generated by shared familial confounding factors or by parental genotypes transmitted to the offspring. If, however, there is an intrauterine influence, then only the maternal exposure would be expected to show an independent association with the outcome. So here are some DAGs that just overlay the negative control outcome onto the previous graph that I had. And so you could see, ideally, a negative control outcome should be chosen, should be an outcome that's chosen such that the set of common causes of the exposure of interest in the outcome is shared with that outcome, that a confounding mechanism is common as much as possible. To the extent that the set of unobserved common causes of A and Y in this graph overlaps with the set of unobserved common causes of A and N, we call the negative control outcome U comparable. This is, of course, an ideal situation that will never occur, but to the extent that you can approximate it, the hope is that it would lead to a tool for detecting unmeasured confounding. And there are some, if N and Y are U-comparable outcomes, with an identical set of common causes that are associated with the treatment, and assuming that N is not causal by, it's not a cause of Y, it's not caused by A, it's an outcome, an association between the exposure and the negative control outcome, when analyzed according to the same procedure used to analyze the original pair of the exposure and the original outcome, would indicate bias in the association of A and Y. So this is a very simple tool that one could use to detect confounding. Likewise, the negative control exposure is a variable that is known not to cause the outcome, but the hope is that it shares as much as possible the unmeasured confounding as the original exposure and the outcome. And I added here an instrumental variable for folks who are familiar with it to show that it actually has a very different structure. It's the inverse of an instrumental variable. I'm not going to go into that just in the interest of time, but if you're familiar with instrumental variable as another tool to deal with unmeasured confounding, this is actually a different notion to that. And so, to the extent that the set of unobserved common causes U of A and Y overlaps with the set of unmeasured common causes between the negative control exposure and the outcome, we call the negative control exposure U comparable to A. How much more time do I have? Okay. And the idea is, again, to look for an association between the negative control exposure and the outcome of interest as an indication as to whether or not you may have unmeasured confounding operating in your analysis. Some other examples of negative controls, very briefly, that have appeared in literature: in occupational radon exposure in miners, the outcome was lung cancer, negative control outcome was COPD. Exposure, flu vaccine again, the outcome being the influenza hospitalization. Negative control there was tetanus vaccine. This is a negative control exposure. Universal Child Credit offers benefits to parents with children less than 6 in Canada. The outcome was family food insecurity. Negative controls were non-eligible families, only with kids greater than 6 years old. And then exposures, and this actually is very natural, in air pollution studies where you might be interested in the association or the causal association between air pollution at week T and the outcome being mortality or hospitalization at time T+1, and natural negative control outcome might be the mortality prior to the air pollution level you're looking at. Negative control exposure is very naturally the air pollution level after the outcome you're looking at. And because of temporality, the causal assumption that the air pollution after mortality cannot causally affect mortality is very natural. And so in time series studies for air pollution, for studying the impact of air pollution on mortality, this is what we call a double negative control design lends itself quite naturally and I think should be used quite routinely. So far I've only talked about using negative controls for detection of unmeasured confounding, and you might naturally ask, could they ever be used once you've actually found evidence of unmeasured confounding? Could you ever go an extra step and actually account for the unmeasured confounding using the negative control? And so, in fact, this is not a new idea. If you're familiar with, it's very popular in econometrics, the difference in differences, DID design. It's actually formally a negative outcome control approach. And so what the idea is, under two conditions, one that one has observed the outcome pre and post exposure for each person or in repeated cross-sectional samples, and two, the association of the unobserved confounder with the outcome is assumed equal across exposure groups and constant over time. Under those two conditions, what you may do is then the approach simply entails estimating the effect of exposure by taking the difference in the outcome between the pre-exposure level and the post-exposure level, and comparing it for the people who receive the active treatment or the exposure of interest to people, the subset of the data of the sample who do not receive that treatment. The approach, the idea is that the pre-exposure outcome, version of the outcome, is formally a negative control outcome. And under this extra assumption, it has been used as a means for adjusting for unmeasured confounding, and this would recover a valid causal effect if, in fact, these assumptions held. Another approach known as the control outcome calibration approach, and this can work with any underlying causal model you might have. It could allow for interactions with covariates that have been observed, but just for the sake of simplicity, due to the interest of time, suppose that the average causal effect were actually known to be additive and constant across the population, just to explain how the approach works. And the idea is that then for each person, if hypothetically you knew what the causal effect were, then you could use it to generate the outcome that person would have had in the absence of the exposure, so-called counterfactual outcome, by simply, for those people who were exposed, you would take off the magnitude of the effect that you hypothesized, and for people who were unexposed, that would be the outcome that you observed. Okay? And the basic idea is that this exposure-free outcome, this potential outcome, or this counterfactual outcome, is in fact a strong surrogate measure of the unmeasured confounder itself, and can be used to adjust for confounding between the exposure of interest and the negative control outcome. And so you're sort of inverting the principle that, in fact, you know that between the exposure of interest and negative control outcome, the association should be null, the causal association should be null. And you use your causal model to predict what the unmeasured confounder might be. And I would adjust, thank you, would adjust for it and to recover that association. And you can play this exercise, and you can then generate all possible values of average causal effects such that adjusting for the corresponding estimated exposure-free outcome minimizes the association between the exposure and the negative control outcome. And we have software for this and available. I think this is my last slide. And this is formally the double adjustment by negative outcome, negative control exposure, Danon. The idea is, again, you're interested in the effect of air pollution at time t on mortality at time t+1 or t here, but the temporal order needs to hold. One can use as a negative control exposure mortality at time t minus. I'm sorry. It might be it. As a negative control exposure, one might use mortality at time t+1, and as a negative control exposure, air pollution at time t minus 1, or maybe I reverse it too. At any rate, having both of them available would actually allow you to completely account for measure confounding in a non-parametric fashion. It doesn't rely on any model. This is completely relying on, is completely design-based. And so the causal effect in such setting is non-parametrically identified under certain rank conditions, restricting the number of levels for the unobserved confounder that can be taken relative to the levels of the negative control exposure and outcome. And I think I'm going to stop here. I ran out of time. Thank you so much.